Hello and welcome back to our presentation on Thyristor family devices, part 3. Myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology, Bandar, East. So, in this presentation, we will see the two member of Thyristor family device, that is GTO and TRIAC, with respect to construction, operating principle, VI characteristics and applications. And course outcome is to identify power electronic devices in the circuits. So, let us see what is GTO. GTO stands for gate turn off thyristor. The name itself signifies that it has got the gate that will be used for turning off the thyristor. So, same gate terminal is used for turning it on when a positive gate pulse is provided, and when a negative pulse is provided, then it turns off. So, this additional feature has the advantage over SCR, which is SCR is considered as a semi-controlled device, whereas the GTO with this additional provision of turning it off becomes more superior in many applications. And GTO is similar to that of the SCR in construction layered structure, that is 4-layer 3-junction PNPN device, and it can be used as switches, rectifiers and voltage regulators. So, GTO was invented by General Electric and included in the thyristor family device in the year 1973, and similar to thyristor, GTO is also a current control device and minority carrier device, bipolar, that is. So, how it is differing from the conventional thyristor is that they are designed to turn off when a negative current is sent through the gate, thereby causing the reversal of the gate current and turning it off. So, during the conduction period, on the other hand, the device behaves just like a thyristor and with very low on state voltage drop. Now, there are several varieties of GTOs, can be classified as symmetric GTOs, asymmetric GTOs and reverse conducting GTOs. So, symmetric GTOs are the one in which the forward breakover voltage and the reverse breakover voltage are equal. If they are different, if the reverse blocking capacity of the GTO is less than that of the forward, then it is asymmetric GTO, and generally this reverse voltage blocking capacity is of the order 20 to 25 volt. And reverse conducting SCR, the third category, is integrated with an anti-parallel freewheeling diode onto the same silicon wafer. So, it will have an anti-parallel freewheeling diode. Is the schematic symbol for the gate turn off thyristor. So, either of these can be drawn. The double arrow one going inside is for the turning on and another for turning off. Operating principle and the working is similar to that of the SCR, thyristor, conventional thyristor. The structure we are seeing is similar to that of the SCR, that is 4-layered structure PNPN from anode to cathode. For turning on, as I said, can be turned on with the positive gate signal IG, and for turning off can be done by either a zero crossing current or by applying a negative gate signal at the same gate that was used for turning on. How it is different is in the structure modification that is done to achieve the turn off capability, and we find a N plus layer here which is highly doped near to the cathode structure. So, these N plus layers are highly doped to make the emitter efficiency high, and it will lead to low breakover voltage. J3 will be leading to low breakover voltage of 20 to 40 volt. This is the construction diagram, and here we find the finger like projection of n plus layer. So these layers in a circular manner they are projecting inside, and they are interdigitated with n plus p plus n plus p plus structure, and thus sorting the anode. So with an sorted anode, it will have some advantage and disadvantage too. It will reduce this tail current time, where it is taking more time to turn off. So if we are making it anode sorted, then this tail time is reduced and it can be turned off faster. VI characteristics is similar to that of the SCR. In the first quadrant, first blocking mode, when anode is made positive with respect to cathode and a positive gate pulse is provided, and when breakover voltage is reached, it will turn on and there will be a small on state voltage drop, and it will increase as load current is increasing. And in the reverse direction, it is blocking state till it reaches the breakover voltage in the reverse direction, and once it reaches that breakover voltage, a large current will be flowing. So it is desired operation is in the first quadrant. Second characteristic is the gate characteristics, where the gate current is plotted with respect to the changing or increasing gate voltage. So here we find applications in inverters, choppers. GTOs are used in motor drives for providing the static VAR compensation or compensator circuits. It is used in AC DC power supplies with high power ratings, and GTO eliminates the need for forced commutation circuitry, because the same gate terminal is used for turning off by providing a negative gate pulse, and hence it will have less cost because it is not making use of commutation circuitry, and voltage source converters make use of GTO. And power rating could be of maximum value. Here we see 6.5 kV and 4000 of ampere of current. These are types of different packaging types of GTO. That's it for the GTO. Next topic is TRIAC. TRIAC is standing for the triode for alternating current. Means current flow will be for positive as well as negative half. That is not possible in the case of semi-controlled SCR. So a TRIAC is a 3-terminal 5-layer semiconductor device with forward and reverse bias characteristics identical to that of the SCR. And equivalent circuit we find here 2 SCRs connected in anti-parallel with a common gate. Gate is interconnected and taken out as common gate terminal, and the two terminals are marked not as anode or cathode because current can flow either way from MT1 to MT2 or MT2 to MT1. So they are marked as main terminal 1 and main terminal 2, and gate is marked as gate terminal. So TRIAC is bidirectional switch because current can flow in either direction, and turns on either with a positive or negative voltage at the gate, and for turning it off we can reduce the circuit current, that is the main terminal current, to a value below the holding current. The voltage and current rating we find 600 volt and 40 ampere of current TRIACs available in the market. For example, here we have one image of stud mounted TRIAC, that is SC40D, one of the company, and 400 volt rating with 6 ampere current. And another we have here BT 136, where this 6 last digit represents the current rating. Similarly, in 139, 9 ampere current. And here we have the cross sectional view of a track. So this is main terminal 1, main terminal 2, and here we have the gate, and here we find the different P1, P2, and P1, N1, P2, N2, and here we have the N3 layer below the gate and N4 here. Now the VI characteristics of the track. For VI characteristics, let's see the operation first, where the main terminal 1 is made negative with respect to MT2, means MT2 is positive with respect to MT1, and MT1 is also negative with respect to gate. So here we have the gate voltage provided. So with this biasing and getting voltage, we find the initial gate current will be flowing from the gate to N2 layer and to the MT1. This will make the current to flow from P1, N1, P2, N2 finally, and it is more sensitive. Similarly, when the gate current is made reverse, then the current at the gate and MT1 terminal we find is flowing from NT2 to NT3 and N2 to N3 layer, and initial current will be flowing from MT2 P1 P1 N1 P2 and N3 here, and after some time it shifts to the right hand side here, that is from P1 N1 P2 N2. Similarly, if the main terminal polarity is reversed, that is MT2 negative and MT1 positive and gate is positive, then we find that current has reversed from its main terminal MT1 to MT2. Current is flowing finally from P2 N1 P1 N2, and last here we see the MT2 negative with respect to MT1, and when it is MT1 is made positive with respect to gate, initial current will be flowing here from MT1 to N2 gate, and this makes the current to flow from MT1 to MT2. So for these 4 mode of operation, we have here in VI characteristics represented these circuits arrangement and biasing, and we find that it is symmetrical in the first quadrant. The VI characteristics is symmetrical in first quadrant and third quadrant. So it is bidirectional and similar characteristics that of the SCR. So it is desired to be operated in the first and the last 4th mode. Now what are the applications of a track? Track find application in control circuits like the electric fan speed regulator, speed control, and smaller motor controls, and high power lamp switching and light dimmers to control the light intensity. Here we have example of the firing circuit for track using a DIAC. So this is the track that will be fired using the current from the DIAC and controls the current flow through the load, and AC power control in domestic appliances. So these are the applications of track. These are the references for further studies. That's it. Thank you very much.